Hey guys, Mr. Backberg here. In this video, we're going to talk about limits and the connection to area. Now, we looked at an example in an earlier video where we had a car that was traveling at a constant rate of 48 miles per hour, and we traveled that speed for 2.5 hours, and that gave us a total of 120 miles covered in that trip. Now, I want to look at this a little bit differently. Because we're traveling a constant 48 miles per hour, we can think about that as a constant function. So I'm going to call that y equals 48. And what I want to do is I want to look at a graph of that equation. So if we draw out an x and a y grid, because we have just y equals a number, that's going to be a flat horizontal line through the y value of 48. And what I want to do is I want to look at what's happening over this 2.5 hours. So that's going to be my x value along the bottom here. So I'm going to say this point right here along my x-axis is 2.5, representing that 2.5 hours. Now what's happening in here is if we look at this graph bounded at that 2.5 and along our x-axis and our y-axis, we're creating a rectangle in here. This horizontal distance, since we're starting at 0 and going out to 2.5, is a distance of 2.5. And this vertical height, since we're up at a y value of 48, this vertical height is 48. Now, if I were to find the area of this rectangle, I would take the length times the width. And if I take 48 times 2.5, I get 120, which is the exact same answer that we got before. And it's really no coincidence that the area of this rectangle and the answer for our total miles covered are the same exact value. Now let's look at this a little bit differently. Instead of traveling a constant 48 miles per hour, let's say our speed changes. Let's say we start off going slow, but then we speed way up and then we slow back down. Now we're still going to cover that same exact 2.5 hours, but instead of that constant speed being 48, let's say that our average speed, our average velocity was 48 miles per hour. Now we just said that the area of that rectangle was going to be the exact same answer as that 120 miles, but now our shape's a little bit different. We've got an irregular shape. So what we want to know is the area underneath this curve still going to be equal to that 120 miles that we traveled? And that's exactly what Newton and Leibniz were considering as they were developing calculus. And they were convinced that it was going to work out. Now things get a little trickier. Finding area of a rectangle is pretty easy, but when we have this irregular shaped object, it's much more difficult to find its area. So what they did was start to break up this area underneath this curve into rectangular chunks, since rectangles are easy to find the area of. And what they found is as they used smaller and smaller intervals, more narrow rectangles, they were better able to approximate the area underneath this curve. So we're going to take a look at an example in here where we approximate area underneath the curve using rectangles. So we're going to use 6 rectangles to approximate the area of the region below the graph f of x equals x squared over the interval from 0 to 3. So I've already got my function graphed out. X squared gives us a parabola graph. We're looking on the interval from 0 to 3, so I'm only looking at the right half of this graph. Now with our 6 rectangles that we're supposed to be drawing out in our picture, we want them to be equally spaced. Now this interval is going from 0 to 3, meaning that that interval has a length of 3. If we want 6 rectangles to fit in that length of 3, well, if I take 3 divided by 6, that gives me an interval length of half a unit. Now I'm going to use something called right rectangular approximation. And what that means is as I'm drawing in these rectangles in my picture, I want the right end point of my rectangle to be a point on the graph. So for example, this first rectangle where we're going from 0 to 1/2, I want the right side of that rectangle to be that point on that graph. So we end up with this little rectangle in here. Now if I go another half over, I want that right end point of that rectangle to be a point on the graph. So I'm drawing in all of these different rectangles. Another half over, and that point on the graph, and we're completing this rectangle in here. And I'm going to keep drawing out each one of these individual rectangles. So here are the 6 rectangles that we're going to use to approximate the area underneath this curve. So now here's what we're going to do. If we look at this very first rectangle, that's on the interval going from 0 to 1/2. So the distance across the bottom, the base of that rectangle, is a distance of 1/2 of a unit long. Now, as far as the height of our rectangle, we said we were going to use the right endpoint on that graph. So I'm looking at this 1/2 as that x value. What I need to do to find the height of this rectangle is I need to take that 1/2 and plug it into my function. So if I take 1/2 and square it, then I'm going to get 1/4. So then if I find the area of that rectangle, multiplying the base and the height together, 1/2 times 1/4 is 1/8, or as a decimal, that's 0.125. Now if I look at the next rectangle, the next sub-interval, that goes from 1/2 to 1. So again, we've got a base distance of 1/2. If I look at the right end point on my interval to find the height of my rectangle, if I take 1 and square it, we're going to get 1. And then to find the area, we go base times height, so 1/2 times 1 gives me 0.5 for an area of that second rectangle. And I'm going to continue this. So our next sub-interval is going to go from 1 to 1.5. Again, that's a base distance of 1/2. If I plug in that right end point, that 1.5, and square it, then that's going to give me 9/4. And then if I multiply base times height, we're going to get 1.125. Now my next subinterval is going to go from 1.5 to 2. So again, our base distance there is 1/2. Using that right end point of 2 and squaring it, the height of that rectangle is going to be 4. 1/2 times 4 is going to give us an area of 2 in that rectangle. Then we're going to have to go from 2 to 2.5. Again, the base distance in there is 1/2. Taking 2.5 and plugging that in to find the height of the rectangle, 2.5 squared is 25/4. And then if I take 1/2 times 25/4, we're going to get 3.125. And then our last subinterval is going to go from 2.5 to 3. So that's this last rectangle in here. Again, the base distance is 1/2. If I take the right end point and plug it in, that's going to tell me that the height of my rectangle is 9. So if I take 1/2 times 9, then the area under that portion will be 4.5. Now what I can do with all of these individual rectangles, all of these individual areas, is I can add those together. So if I take all of these area values and add them together, we're going to get 11.375. Now what I want you to notice about this picture, using this right rectangular approximation, we've got some portions of our rectangle that are overhanging that graph. They're going above the graph. So this 11.375 is an overestimation of what this area was going to be. We could do something similar where we use left rectangular approximation. So if I get rid of these blue rectangles in here, left rectangular approximation is where the top left end point of our rectangle is a point on our graph. So we would end up getting a picture that looks something like this. And what we can see is that there are some gaps. It doesn't quite fill in all of the areas that we need it to fill in. Now, I'm not going to show you all the math, but what we would end up getting here is if we found the total area using left rectangular approximation, it would be 6.875. Now, if we averaged these two values together, we end up getting 9.125 as the average area underneath that curve, and that's actually really close to what the actual area is. The actual area is 9 units. So what's happening in here is because we're only using 6 rectangles to approximate this area, there's some degree of error with both our right rectangular approximation and our left rectangular approximation. So if we could make those rectangles smaller and smaller and smaller so that there's not as much overhang or not as big of a gap underneath that graph, then that's going to give us better and better approximations as to what the actual area is. So we can think about that as using a limit of an infinite amount of rectangles underneath that curve to try to fill it in as best as possible to give us the best approximation of what that actual area underneath the curve is. That's going to be it for this video. Thanks for watching.